Okay, now we're going to get into something called specific heats. What are specific heats? Specific heats are some properties that we're going to be using when we deal with solids and gases, basically and liquids as well. This is a property that is used largely when we don't have any phase change going on. So let's go ahead and get into this, and we'll specify a little bit more about when we use these properties as we go along. So specific heat. The word specific heat, basically, it's a property that says it is the energy required to raise the temperature of a unit mass of a substance by 1 degree. So if I have 1 kilogram of water, it would be the energy required to raise the temperature of 1 kilogram of water by 1 degree. And there's two basic types of specific heats that we'll be looking at. One is specific heat at constant volume, which is the energy required to raise the temperature of a unit mass of a substance by 1 degree as the volume is maintained constant. And then there's also specific heat at constant pressure, which ends up becoming, the definition is this, the energy required to raise the temperature of a unit mass of a substance by 1 degree as the pressure is maintained constant. Right? They're not going to be, they're not the same thing. They're both different numbers. Characteristics of specific heats. We call them C sub B and C sub P. Specific heat, constant volume is C sub B. Specific heat at constant pressure is C sub P. They're expressed in terms of properties and therefore are properties themselves. The specific heat of a substance depends on the state, which is in general specified by two independent intensive properties. The mathematical expressions for C sub B and C sub P are property relations, and as such are independent of the type of process, right? The mathematical relationships are valid for any substance undergoing any process. So basically, C sub B is related to the change of internal energy with temperature, and C sub P is related to the change in enthalpy with temperature. So here are the definitions. C sub B is equal to du dt at constant volume, and C sub P is equal to dh dt at constant pressure. Let's take a look at it. Remember the example problem we did earlier, right? Well, where we looked at a first law analysis of heat being added to a tank versus heat being added to a piston cylinder assembly. So let's come back to that example and let's look what's going on here. This is saying the specific heat for this substance is, if I were to add, so this is a constant volume tank, right? And I have 1 kilogram of mass in here, and I want to raise the temperature of that 1 kilogram of mass 1 degree Celsius. In this particular case, if it takes 3.1 kilojoules of energy to raise 1 kilogram of this substance 1 degree Celsius at constant volume, we would say the specific heat is 3.12 kilojoules per kilogram Celsius. In this example, I have this heat being added that actually causes the piston to rise, which is a constant volume process or a constant pressure process. So if I were to look at the amount of energy that's required to raise 1 kilogram of this mass 1 degree Celsius during constant pressure, it would be 5.19 kilojoules. So that means that the specific heat at constant pressure is 5.19 kilojoules per kilogram Celsius. Also, it's important to note, specific heats are temperature dependent. So as temperature changes, specific heat also changes. For example, for air, specific heat at 300 Kelvin is 0.718. At 1000 Kelvin, it's 0.855. So what we're going to do now is we're actually going to take specific heats and we're going to use them for the case of ideal gases. right? This is where thermo starts to diverge a little bit in terms of the equations, because we're going to be, as we develop in all these different chapters, we're going to be developing new equations. And these equations are all valid under certain assumptions, and that's important to remember, is that they're valid under certain assumptions. So when you guys formulate equation sheets, be sure that you list the assumptions for which these equations are valid. If not, what happens is you just start having all these equations and not knowing how to apply them. And a lot of times what happens is that you just sort of throw equations at a problem, hoping for the best instead of picking the one that is appropriate due to the assumptions of the problem. So let's look at something here. We're going to look at quantifying internal energy and enthalpy of ideal gases. Okay? Because if you think about it, we've used the ideal gas law. PV equals mRT. That relates temperature, volume, and pressure together of an ideal gas. And we've done that in many problems, right? If you think about it, the problems we've done so far is we've developed enthalpy and specific volume and all the properties for phase change substances like water and refrigerant, and we've been using the tables for that. For ideal gases, we've really only been quantifying pressure, volume, and temperature together using the ideal gas law. What this does, now we're going to go ahead and we're going to advance and go forward and now start quantifying internal energy and enthalpy also for ideal gases. We haven't done that yet. Well, for an ideal gas, internal energy is a function of temperature only. So let's look at internal energy first. And that's something we haven't heard yet, because I've always told you, you need two properties to evaluate all other properties. But in the case of an ideal gas, the assumption, this is only valid for ideal gases. If you were to say that it is for phase change substances, like you have a process going on where water is changing phase, and you're telling me, well, you said internal energy is a function of temperature only. Internal energy is a function of temperature only for ideal gases only. Okay, so basically, if we rewrite that, we could find that internal energy is a function of temperature only. If you remember, the definition of specific heat is du dt. So if you think about it, internal energy can be quantified by integrating the specific heat at constant volume over temperature. I'm going to go ahead and show you that since internal energy is a function of temperature only, enthalpy is also a function of temperature only. Only for an ideal gas, though. Watch. Enthalpy is equal to internal energy plus pressure times specific volume. If I have an ideal gas, I can replace, right, P nu is equal to RD, only for an ideal gas. Therefore, enthalpy equals U plus RT. Therefore, concluding also that enthalpy is a function of temperature only, but only for an ideal gas because I use the ideal gas law. Right? It's important that we understand our assumptions. So let's come back to quantifying internal energy and enthalpy for an ideal gas. CV is equal to du dt. Cp is equal to dH dt. So I'm going to rearrange these equations where I get in differential form du is equal to Cv dt and dH is equal to Cp dt. I'm going to go ahead and integrate it now, right? By integrating it, I get that delta U is equal to U2 minus U1. Basically means integrating the specific heat at constant volume as a function of temperature, right, over the temperature range. Same thing for delta H. Delta H equals H2 minus H1. What happens is I'm integrating that over a certain temperature range. for Cp. So basically, my change in internal energy is going to be equal to the integration of the specific heat as a function of temperature over the temperature range. My change in enthalpy will be equal to the integral of the specific heat at constant pressure over its temperature range. Now, there's two ways I'm going to evaluate this integral. One is assuming the specific heats to be constant with temperature. One assuming this constant heats to be variable with temperature. What do I mean by that? That means that if I assume that specific heat is not constant, is constant with temperature, it means it is not a function of temperature. It means specific heat is at a fixed value, and it doesn't matter what the temperature is. Right? So that means that I can quantify delta U, and I can go ahead and specify a value for specific heat, constant volume, and a constant pressure, right? H for Cp and U for Cv, and I can specify a value that I believe is constant over a temperature range. Now, it's never constant, right? But let's say here I have a graph, right? Cp on the y-axis and temperature on the x-axis. Here's a here's a temperature 1 and a temperature 2. This is how the specific heat might vary between 1 and 2, but what I'm going to do is just go ahead and take the average, take the specific heat at T1, the specific heat at T2, and come up with an average. And what I'll do is that since if I go back to the integral, if I assume this to be constant, the result ends up being C sub V times the change in temperature. Where I assume some average specific heat value between the two temperatures, assuming that the temperature range is not significant, meaning that I'm not going ahead and assuming the specific heat to be average for a great differential range of Cp. So again, I end up that my change in enthalpy is Cv delta T, and my change in internal energy is Cv delta T, and my change in enthalpy is Cp delta T. Now, what happens? Oh, I'm sorry, excuse me. I'm going to go ahead now and by advancing to the next slide, I wanted to show you how these specific heats relate to each other for an ideal gas. Right, we said that H is equal to U plus P nu, and we take P nu and we replace it with RT according to the ideal gas law. Now, if I take the differential of that, I get the following. dH is equal to du plus R dt, since R is canceled. I can replace dH with Cp dt. I can replace dV or du with Cv dt. And then I have plus RT there. What happens is the dt's cancel out, and I get that only for an ideal gas, Cp is equal to Cv plus the gas constant. And this is, again, only for an ideal gas, because I used the ideal gas law to show this. Now, ideal gas specific heats, where do you find values? Well, in table A2, there's 3 different ones. There's table A2A, which shows the specific heats for various gases at a fixed value of 300 Kelvin. Table A2B gives you specific heats for 6 different common gases and tabulates those values from a range of 250 K to 1000 K in increments of 50 Kelvin. In table A2C, gives you the constant pressure specific heat for various common gases expressed empirically as a fourth order polynomial. Right, so you'd have to integrate that one to find the specific heat if you wanted to account for the change in the temperature. But you'd be happy to know. So anyway, these are, I'm sorry, let me slow down a little bit. Here's here's table A2. Again, you have all these different kinds of gases. It gives you the gas constant, the specific heat at constant pressure, specific heat at constant volume, and K, all evaluated at 300 Kelvin. Table A2B. These are just 3 of the 6 gases it has it for. So here's air, for example. If I go down, I see increasing temperature in increments of 50 Kelvin. And it shows how the specific heat at constant pressure and constant volume change as you increase in temperature, including this factor called K, which we'll talk about a little bit later. Just as a prelude, K is something called the specific heat ratio, which is just a ratio of the specific heat at constant pressure divided by the specific heat at constant volume. And finally, table A2C, as mentioned earlier, is just a specific heat at constant pressure given to you in terms of an equation, empirical correlation that was determined based on experimentation, where these constants A, B, C, and D are quantified under here on the table for various gases. Now, if we wanted to go ahead, we can also quantify the the internal energy and enthalpy of ideal gases, also by using what we have as called ideal gas tables. So if you look in your book, there are ideal gas tables, which are basically tables A17 through A25. If you go to those tables, you'll notice that for all these gases, all the properties are listed according to temperature. As I mentioned earlier, enthalpy and internal energy for an ideal gas are functions of temperature only. Now, there are other things in here. You see this PR, this nu R, and this S superscript 0. We're going to be covering those at a later time in another chapter. Right now, what I'm most concerned with is you guys seeing enthalpy and internal energy all based on temperature. Now, for air, you can see that these are all based on mass, right? All the specific properties are based on mass. But when you go to some other of these tables, like for example, carbon dioxide, which is table A20, these are all listed in molar basis, right? You can see H bar. H bar represents the fact that that is a specific enthalpy on a molar basis. So again, everything is based on temperature, but as you see, these values are quantified according to mole per mole, not per mass. Not a big deal. All you need to do is use molarity to convert that back to mass basis from molar basis if you wanted to do it mass basis. So, if you wanted to use these tables to quantify the change in internal energy or the change in enthalpy, it's pretty simple. You would just basically take the temperature at each state, find the corresponding internal energy for internal energy. So if I wanted to find, for example, the change in internal energy for an ideal gas going from state 1 at temperature 1 to state 2 at temperature 2, you would just take T1, find the corresponding internal energy, find T2, find the corresponding internal energy, and take the difference. Same thing for enthalpy. Now, what's great about that is that these tables are a very direct way to figure out how to figure out what the change in internal energy and enthalpy is assuming that my specific heats change with temperature. What do I mean? There's two basic assumptions you can draw. One is assuming, for example, if you wanted to find a change in internal energy, you would assume that your specific heat is constant with temperature. So when you work out the integral, right, when you work out this integral, delta U is equal to the integral of CVT dt. Well, if CV is constant with temperature, then this would just factor out of the equation, and you would end up with a specific heat at constant volume times the change in temperature. But what if you wanted to go ahead and include the fact that specific heat changes with temperature, right? I mean, it really does. If you go back to, sorry, let me rewind a little bit. If we go back to this table, for example, table A2B, it shows that, for example, air, as I increase in temperature, 250, 300, 350, 400, so forth, my specific heat's actually increasing with temperature. But if I don't have a big temperature increase, like let's say the temperature increases from 250 to 450, my specific heat increases from 1.003 to 1.02. Right, that's an increase of specific heat. That's an increase of 17, or 0.01. That's an increase in 0.017 over a number of over a range of 1, which is basically almost like saying it's a change in 17 over a factor of 1,000, which is about 1.7% difference, right, between here and here. So if I wanted to find the internal energy change between, or the change in internal energy or enthalpy, right, this is Cp, so my change in enthalpy would be equal to, if I wanted to assume constant specific heats, it would be delta H is equal to Cp, T2 minus T1. So if I want to evaluate that, I would take the average Cp between the two temperatures. Let's say I'm going between 250 and 450 Kelvin. It would be 1.003 plus 1.02, and I take the average between the two, which is about 1.011, and then I'll go ahead and just multiply that by the temperature change, 250 or 450 minus 250. And that will give me the change in enthalpy of air between the temperature of 250 degrees and 450 degrees at constant, or at a constant specific heat. But what if I didn't want to do constant specific heats, right? What if I wanted to account for the variation in specific heat? I would have to go to this slide and go ahead and say, okay, well, I have air, A, B, C, and D are these numbers. I'm going to plug it into this number. I'm going to go ahead back to my equation, where delta H is equal to the integral of Cpt dt. Okay, I'm going to plug in that function for Cp, integrate this from T1 to T2, and evaluate that way. It becomes a little bit of a hassle, right? So there's a much easier way to do that. These tables that we just looked at, these tables give you internal energy and enthalpy as a function of temperature, accounting for the specific heats changing, right? So these basically account for the variation of specific heats, CV and CP, accounts for the variation with temperature, right? So that means that this value of enthalpy of 199.97 200 degrees includes includes the fact that includes my CP. So basically it's saying that enthalpy at 200 degrees is equal to the specific heat at 200 degrees times 200 degrees, or not degrees, but times 200 Kelvin. So it takes the specific heat at 200 Kelvin and multiplies it by the temperature 200 Kelvin to get you that number. This number at 250 equals the specific heat at constant pressure evaluated at a temperature of 250 Kelvin multiplied by 250 Kelvin. Basically, these all account for variations in specific heat. So what I can do is I can just go to the table, right? I can go to the table. Let's say I wanted to find delta H. Delta H is equal to the integral from 1 to 2 Cp of T dt. What I could do is go to the tables and find H2 at T2 and subtract H1 at T1. This is equal to that. All right? So basically, if I wanted, what I'm getting at is if I want to account for the variation of specific heat, I will go ahead and use the tables. If I wanted to go ahead and assume my specific heat to be constant, I'm going to go ahead and factor out CV from the integral and just use it as CV delta T. When to do it, it's an engineering decision. It depends on the information available and the desired precision of your calculation. So there's often more than one method that can be used. To be safe, you should always state clearly which method you're using and the assumptions you're making, right? So basically, the two assumptions are constant specific heats and variable specific heats. Those are the assumptions you're going to use when you're looking at an ideal gas and you're trying to find the change in enthalpy and the change in internal energy of an ideal gas. It's another assumption you need to make. Are you going to assume the specific heats to be variable, or are you going to assume the specific heats to be constant, i.e. either constant or variable specific heats? Constant specific heats means you find enthalpy change and internal energy change using this method. Variable specific heats means you find the change in enthalpy and the change in internal energy using this method. A lot of times in thermodynamics, the word constant specific heats or variable specific heats becomes super complicated and not super complicated, but confusing. But basically what it comes to is, if I'm going to assume constant specific heats, my change in internal energy and enthalpy are the following. Some average CV delta T for internal energy, or some average CP times the change in change in temperature. If I'm going to assume variable specific heats for internal energy and enthalpy, that means I go ahead and go to the table. I go to T2, I find the corresponding internal energy, and I subtract the internal energy that I find according to T1, the values that I find in tables A17 through A25. The change in internal energy would be the enthalpy at state 2, depending on what the temperature at state 2 is. Now remember, this isn't H2 times T2. This is H2 evaluated at T2 minus H1 evaluated at T1. Okay, I hope that's clear. We're going to go ahead and go through a few example problems to help clarify this point.